In this chapter, we're going to look at sound waves. First, let's look at how sound waves are produced. Sound waves are produced by vibrating objects. Produced by vibrating objects. For example, take a tuning fork. So what happens is when the tuning fork vibrates, when it expands, the molecules over here will compress. Okay, as it goes back, the molecules relax, and then we have compression, relaxation, and so on. So sound wave is the propagation of the compression and relaxation of the molecules. So you've got high pressure, low pressure, high pressure, low pressure, and so on. So in the case of sound waves, what happens is it is the compression and the relaxation or rarefaction of the molecules that propagates through air. Okay, so this compression is as the compression refers to high pressure, relaxation represents low pressure. So you can say that what propagates through space in the case of sound waves is the variation of the pressure. Okay, so the physical quantity that propagates, or you can say varies as a function of position in time, as a function of position in time, is the pressure of the molecules, is the pressure of the molecules. Okay, so it is the high pressure, low pressure, and so on of the molecules that travels through space. Okay, now if you look at the sound wave as a function of position, this is how the molecules are changing as a function of position. You see this distance between two consecutive maximums, between two consecutive compressions or high pressure locations, is called the wavelengths and denoted by lambda. Okay, so this distance between consecutive compressions is called the wavelengths. Now if you look at a particular molecule, what's happening is the molecules are just moving back and forth like this where they are. The molecules are just moving back and forth where they are, and the time taken for one complete cycle is called the period. Okay, so the distance between consecutive compressions is called the wavelengths, and we're again denoted by lambda, and the time taken by a molecule to make one complete cycle is called the period. The time taken by the molecules to make one complete cycle is called the period. Okay, the period, and we're again represented by capital T. Okay, and of course the number of cycles, frequency, is the inverse of the period, so we have the frequency of the wave equals 1 over the period. And as we've seen before, unit of frequency is hertz. Okay, unit of f is 1 over second, or hertz. Okay, now let's look at the speed of sound. The speed of sound, let's represent it by v. Okay, the speed is a constant, so you can say it is distance divided by time. Okay, so if you take one cycle, the distance is the wavelengths, and if you take one cycle, the time taken is the period. But 1 over period is frequency, So this is wavelength times frequency. So the formula for the speed of sound, like any other wave, is simply wavelength times frequency. Now, sound wave is a longitudinal wave. There are two kinds of waves. They're called longitudinal and transverse waves. Let's distinguish between these two waves. Let's look at longitudinal and transverse waves. Transverse waves. Okay, let's look at transverse wave first. A transverse wave is a wave where the direction of movement of the molecules is perpendicular to the direction of propagation of energy. For example, take an ocean wave. The molecules are moving up and down where they are, okay? But we know that the energy is propagated perpendicular to the movement of molecules parallel to the surface of the water, let's say towards the beach, okay? So a transverse wave is a wave where the movement of the molecules is perpendicular to the direction of propagation of energy. If you take an ocean wave, the energy is traveling parallel to the surface of the water, but the molecules are moving up and down. So this is a wave where the direction of motion of the molecules is perpendicular to the direction of propagation of energy, to the direction of propagation of energy. So for ocean wave, you get molecules moving up, but the wave travels parallel to the surface, and so they are perpendicular. Therefore, ocean wave is a transverse wave. And the other type of wave is longitudinal wave. Okay, in this case, the direction of movement of the molecules and the direction of propagation of energy are parallel. Let's say the molecules are moving back and forth like this, and the energy is propagated this way. Okay, so this kind of wave is a wave where the direction of motion of molecules, direction of motion of molecules is parallel to the direction of propagation of energy, direction of propagation of energy. So you see, a very good example of this kind of wave is sound wave. In a sound wave, what happens is the molecules are just moving back and forth in this direction, and the energy is propagated in a direction parallel to the movement of molecules. So sound is longitudinal wave. So according to the definition, sound is a longitudinal wave, which means the direction of movement of the molecules is parallel to the direction of propagation of energy. Okay. Now let's look at classification of sound. Classification of sound that's based on the frequencies. Okay. Now, frequencies that can be detected by the human ear are called audible waves. So audible sound waves, these are sound waves that can be detected by the human ear. Okay, so those sound waves that can be detected by the human ear are called audible waves, and the range of frequency for these waves is from 20 Hz to 20,000 Hz. So if the frequency of the sound is between 20 Hz and 20,000 Hz, it can be detected by the human ear. And then we have the infrasonic sound wave. Those are sound waves whose frequency is below 20 Hz. Okay, these are frequencies below 20 hertz. These are frequencies below 20 hertz. Okay, a good example is earthquake. Earthquake vibrates at a speed of less than 20 cycles per second, so you can feel it, but you can't hear it. Okay, so if the frequency, which is number of cycles per second, is less than 20 times per second, it cannot be detected by a human ear. Okay, it's called infrasonic. And then on the other range, we have the supersonic sound waves. These are frequencies above 20,000 hertz. These are sounds whose frequencies are above 20,000 hertz. Okay, if a sound has a frequency above this one, it cannot be detected by the human ear, but dogs can detect frequencies above 20,000 hertz. So these are the three types of sound we have. Audible frequencies are the frequencies that can be detected by the human ear, and they range from 20 hertz to 20,000 hertz. Infrasonic frequencies are the frequencies whose frequency is less than 20 hertz, and so they cannot be detected by the human ear. Supersonic waves are frequencies whose frequencies is greater than 20,000 hertz, and they cannot be detected by the human ear. Okay, now let's look at the relationship between the properties of sound and the sensation of human ear. Sensation of human ear. Okay, all right. Now there are two kinds of sensation of the human ear, and they are loudness and pitch. And the wave property has two properties. It has frequency, it has amplitude. Okay, frequency is how fast the molecules are vibrating back and forth, and amplitude is how vigorous the molecules are vibrating. Now the amplitude is related to the loudness of sound. So loudness of sound, this is related to the amplitude of the sound. Amplitude, that is how vigorously the molecules are vibrating. How vigorously the molecules are vibrating. So the loudness of sound has to do with amplitude, or how vigorously the molecules are vibrating. And then the other property is pitch. Pitch has to do with the frequency of the sound. The greater the frequency, the greater the pitch. So this one is related with the frequency of the sound. Okay, the frequency of the sound. So this is the relationship between human sensation and properties of sound. Okay, a wave has a property of amplitude and frequency, or wavelengths. Our sensation has a property of loudness and pitch, and so loudness is related with the amplitude, with how vigorous the molecules are vibrating, and pitch has to do with how fast the molecules are vibrating back and forth. So pitch is related with frequency, while loudness is related with the amplitude of the sound. Now we're going to look at how the speed of sound depends on temperature. Okay, we're going to look at dependence of speed of sound. We're talking about air. Speed of sound in air with temperature. Let's see how the speed of sound depends on temperature. Okay. Last semester, if you remember, we have learned two expressions for the energy of a molecule. One is, of course, the formula for kinetic energy. If you don't have potential energy, we can say the whole energy is kinetic energy. So the energy, if there is no potential energy, in the case of ideal gas, you can say the formula for kinetic energy is half mv squared. So the energy is proportional to the square of the speed, okay? The energy is proportional to the square of the speed. And if you remember, the energy of a molecule is also related with temperature of a gas is, you remember, it's 3/2 nRT. So it's proportional to temperature. So you've got energy proportional to temperature. So this tells you the speed and the temperature are related. The energy is proportional to the square of speed. It's also proportional to temperature. So that tells you the temperature is proportional to the square of the speed. Okay? So, or the square of the speed is proportional to temperature. Or we can say the speed is proportional to the square root of temperature. Okay? So this implies the ratio between the speed of sound and the square root of temperature is a constant. Okay? So what this means is, well, when temperature changes, the speed will change, but this ratio remains a constant. So if you take two states, what this means is the first state, V1 over the square root of T1, equals the second state. If the temperature changes to T2, the speed will change, but this ratio will remain a constant, okay? The ratio between the speed and the square root of temperature will remain a constant. Now, so to calculate this ratio, we just need one state because it's a constant, but there is one state we know. The speed of sound at 0 degrees centigrade is 331 meters per second. Speed of sound at 0 degrees centigrade, but we're going to use Kelvin, or 273 degree Kelvin, is 331 meters per second. So if we take this to be our second state, what we have is T2 is 273 degree Kelvin, and V2 will be 331 meters per second. Okay, so if we go back to our ratio, we have now we don't need the subscript, square root of temperature, well, and then we have V2 over square root of T2. Okay, if you take this state to be this one, because a constant, doesn't matter what state you use, this would be 331 meters per second divided by square root of 273. Okay, moving to the other side, we have the following. The speed of sound equals 331 meters per second square root of T 273. Now remember this in degree Kelvin, so let me say this is in degree Kelvin. All right, so this is the formula for calculating the speed of sound as a function of temperature. All right, now probably most of the time we'll be given the temperature in degree centigrade. Okay, so you can just add 273 to change degree centigrade to degree Kelvin. Okay, you can use the following formula: degree Kelvin equals degree centigrade plus 273. Okay, so if you're given the temperature in degree centigrade, you have to convert to degree Kelvin before you can use this formula. Or if you want, you can say, you can replace this in terms of temperature, in terms of degree centigrade. This one, degree Kelvin, equals temperature in degree centigrade plus 273. Okay, if you do that, we get the following formula: the speed of sound equals 331 meters per second square root of, we replace this by this one, temperature in degree centigrade plus 273 divided by 273. Okay, and that implies the speed of sound equals 331 meters per second square root of 1 plus temperature in degree centigrade divided by 273. Okay, so if you want to use the temperature in degree Kelvin, you have to use in degree centigrade, you have to use this formula. But the other option is you can just change the degree centigrade, degree Kelvin, and use this formula. All right, so that's how the speed of sound varies with temperature. Now let's consider an example. Let's say a tuning fork vibrates, let's say 1000 cycles per second. Okay, so the question is, calculate its wavelengths at a temperature of, let's say, 20 degrees centigrade. All right, now given the frequency of the tuning fork, the frequency is 1000 cycles per second, or 1000 hertz. We're being asked the speed at a temperature of the wavelengths. We're being asked for the wavelengths at T equals 20 degrees centigrade. Okay, so we're going to use the formula for the speed of sound. V equals frequency times wavelengths. We can calculate the wavelengths as the speed divided by the frequency. Okay, but first we need to calculate the speed to calculate the wavelengths. Okay, since we have the temperature, then we can use the speed of sound. We can calculate the speed of sound using the formula V equals 331 meters per second, square root of 1 plus temperature in degrees centigrade divided by 273. Okay, so that gives us 331 meters per second, square root of 1 plus 20 over 273. Okay, that's going to be approximately 343 meters per second. Okay, now that we have the speed at temperature of 20 degrees centigrade, now we can calculate the wavelengths using this formula. Okay, so we've got wavelengths equals speed divided by frequency. We just calculated the speed to be 343 meters per second. We divide that by the frequency, 1000, so we get the wavelengths to be 0.343 meters. Okay, so this is the speed of sound in air. Now let's look the speed of sound in fluid and the speed of sound in metals. First, let's look at speed of sound in fluids. Speed of sound in fluids. Now, the speed of sound in fluids depends on two factors. It depends on what you call the bulk modulus. Okay, I don't know if you remember from last year, but modulus is stress divided by strain. Okay, stress is force over area. We discussed this last year. Stress is force over area. Now for bulk modulus, what we have is a change in volume. Let's say it's the case where the force is applied perpendicularly through the entire surface area. Okay, so you get this force acting on objects throughout this entire surface area. Okay, and the stress would be the force divided by the surface area. Okay, and then we have the strain is the change in volume in this case. Okay, the strain is change in volume divided by the volume. So the modulus, which you call the bulk modulus is stress, which is force divided by area, and then the strain, that's the change in percentage change of the volume, is delta V over V, and since the delta is always negative, put a negative sign over here. So it's just a review for the bulk modulus from last year. Now, the speed of sound depends on this bulk modulus. Okay, the speed of sound is proportional to the square root of the bulk modulus of the fluid. It's also inversely proportional to the square root of 1 over density of the fluid. So rho is density and P is bulk modulus. Actually, the speed of sound in a fluid is given by the square root of bulk modulus divided by the density. So this is a constant you can find in tables in textbook. Okay, for example, if you take water, you'll find this number in a table in textbook, and take the density of water, which is 1000 kilograms per meter cubed. So you can calculate the speed of sound using this formula. Okay, so that's how we calculate the speed of sound in a fluid. From a table in textbooks, you have to find the bulk modulus of the fluid and the density. Okay, so all you need is the bulk modulus and density to determine the speed of sound in a fluid. Okay, next let's look at speed of sound. Speed of sound in a metal. This one also depends on a modulus, but in this case it depends on Young's modulus. Young's modulus usually applies for wires, so let's look at Young's modulus first. So Young's modulus, if you remember, a modulus is stress divided by strain. Okay, so in this case usually applies for wires. It applies for cases where the force is parallel to the length of the meter. Okay, so you apply force over here. This is the cross-sectional area over here. Let's say this is the length, and then this will expand. That's the change in the length over here. Okay, so the stress is force divided by the area, the cross-sectional area over here, and the strain is the change in length per unit time, per unit length, which is delta L divided by L. And so the Young's modulus is defined to be the stress, which is force per unit cross-sectional area, and then the strain is percentage change of the length. This is what you call the Young's modulus of a metal. All right, so the speed of sound is proportional to the square root of the Young modulus of the metal. It's also proportional to the square root of 1 over density of the metal. So we have the following relationship. The speed of sound actually equals the square root of the Young modulus of the metal divided by the density of the metal. Okay, so that's how we calculate the speed of sound in metal. All you need is these two numbers where you can find in textbooks. Okay, the Young modulus, you can find it in a table in a textbook. The same thing, the density, you can find it in a table in a textbook, and the ratio will give you the speed of the speed of sound in the metal. You'll see that the speed of sound in a fluid and metal is actually much higher than the speed of sound in air.